Hi, so today let's talk a little bit about generative models. So, what are generative models? Well, generative models, as the name suggests, generate. What do they generate? The data itself. So, let's say we have training data, right? And we call this training data P of data, and let's say this training data gives us this distribution over images. And now this is obviously a very high dimensional distribution because the images are high dimensional, but let's assume that this training data is giving us a distribution. And what we want to do is we want to learn a model, P model of X, which is as similar as possible to P data of X, such that we can then sample from that model. So ideally we want to learn a model, P model of X, which is similar to P data of X, and we'll then be able to sample from this distribution, meaning generate samples from the distribution P model of X that we learned. Generative modeling usually is an unsupervised way of learning because you don't really need the labels themselves. What you need are the x's, the data points, but not the y's, right? So you don't need the y's. You can just deal with the x's. And like I said, the goal is that given training data, we want to generate new samples from the same distribution. And to do that, we need to learn the probability distribution of the training data. And this whole session today is about how to do that. So, I'll first start with a few examples. For example, this is an example called Lyrebird. They were a speech company back in the day when GANs were popular. And what they did was they kind of invited, a guest to their talk show. And the host then called the guest's mother and made her talk to, this generated voice. And the mother was fooled. And I think at the time it got very popular and then later acquired. These were again one of the first high resolution images ever generated, and this was generated using a GAN using this paper. So if you go to this paper, you can check what this paper is about. But essentially these are all fake images. None of them are real. None of those people actually exist. They're all generated from the minds of let's say an algorithm of data. And it got so popular that even NYT, New York Times, featured it, right? So I'll just go out of this here. So what New York Times said was that, these people may look familiar, like the ones you see on Facebook or Twitter, or whose product reviews you've read on Amazon, or dating profiles you may have seen on apps like Tinder. And they look stunningly real at the first glance, don't they? But they do not exist. And they were born from the mind of a computer, and the technology that makes them is improving at a startling rate. And this article was written, long time ago. This was written on the 21st of November 2020, designed to deceive. Do these people look real to you? And what they also do here is, and the reason why I'm showing you this article is one, because obviously it's important, New York Times covered it, and they have this slider. So this slider is like, let's say, condition, right? So later we'll talk about not just models from where we can sample data, but how can we sample that data when we have a condition. And here the condition is, age. So low age and high age, so from a boy to an old man. Similarly, the eyes, how open the eyes are. In this case, it's the perspective, so how the person is facing. And here the mood, right? So here it's like neutral to serious, and this side it becomes more and more happy. Similarly, gender, so from female gender, you can go all the way to a male gender, and race and ethnicity, right? So these are things possible, and the article then goes on to talk about, what can you do to tell if the images are actually generated or not. And this is from a long time ago. That doesn't really hold all of them, but yeah, it's an interesting article if you are interested. But the topic is not about deepfakes. It's about generative models, and this happens to be one generative model. Okay, I'll go back to full screen. So this was the GAN demo, right? And the topic today will touch GANs and VAEs. So we'll talk about generative adversarial networks and VAEs, and then we'll talk about diffusion model. And this is what we're going to do this week. And what are we going to do? We're saying that, okay, you have your images and your labels. So let's say this is an image which we represent as a vector. This is a single number, let's say the class. But what we've been doing till now is we've been kind of predicting P of y given x, conditional. So you're marginalizing that x out of this joint distribution of x and y. But here what you're predicting is P of x itself. So it's the joint distribution. It's harder because now it's a higher dimensional distribution that we are having to predict and model. And we don't need y, right? So and here we're not able to marginalize x. We need all the dimensions of x. We cannot kind of sum them up and reduce the dimensions of x. We need all the dimensions because we need, let's say, 1000 cross 1000 images, right? So 1000 cross 1000 means your vector that you're generating really has to be 10 to the power 6. 10 to the power 6 cross 1, because you have a million entries, right, in this vector. Only then you're able to generate an image such as this one. And now if you were to, let's say, generally classify generative models, you have these things called as explicit and implicit, and GANs actually happen to be implicit models because we don't do things explicitly, and we're gonna check today why. But the explicit model is, let's say, the variational autoencoder, which we will also talk about this week. So variational autoencoder, and then other simple things like Gaussian mixture models, so GMMs and so on, are all explicit because you explicitly define the distribution and solve for it. But here in the cases of algorithms such as GAN, we indirectly learn that from data. So explicit means the probability density P model of x is explicitly defined and solved for, and here it's not explicitly defined and solved for, rather is learned through indirect interactions with the model. And like I said, what we are interested here are variational and GANs. Now, this is just general information about GANs. Was introduced by Ian Goodfellow in 2014. Since then have been used for many things, and Benjo thought it holds the keys to the universe. It doesn't. People don't use GANs anymore because we have the mod, but we need to understand it to know how we started, how GAN does it, what were the improvements, so that we have a continuum. This is a video I recommend you watch because it's from the mouth of the horse himself. And this is another, so it generates voices, the kind I was talking about. And here there are some tips on training GANs. GANs are difficult to train. I'll talk about why they are more difficult than others. So what is a GAN? GAN, generative adversarial network. The idea in a nutshell is to make two networks compete with each other in a mini-max game. The generator tries to fool the discriminator, and by creating more and more realistic images, and the discriminator tries not to be fooled by the generator, right? So an analogy, let's first think about the analogy, easy to think, is where we have, let's say, police and we have some crooks. And what are these crooks doing? They are generating, let's say, counterfeit notes, right? So they're generating, let's say, 500 rupee notes. And now what will happen is, in a system, there is one trivial, let's say, equilibrium where the police is so powerful that there are no crooks. But for a moment, so that's a mode collapse. Let's not talk about it. Let's say the crooks generate and put some, notes in the ecosystem, in society. So these 500 rupee notes, and they're putting it into society. And then police is looking at, the police has kind of found them, and then they remove them, and they maybe find some of the crooks. And then what happens is, there's a feedback loop, right? So the police is then making these crooks more powerful because they're kind of trying to then make better, let's say, notes so that the police is confused, right? So they're putting more effort into creating more and more realistic notes. And then we also have our real notes, right? The ones actually printed by the government, by the Reserve Bank of India. So these are our data set. And then this is what, and the crook is actually our generator model. And the police is actually the so-called discriminator model. And what is the police doing? It is basically saying, is my note real or not? If it's not real, it's going to punish the crook. It's going to punish the generator. If it's real, if the police cannot distinguish between real and fake, then then that's another equilibrium. So what is the equilibrium? The equilibrium is when the crook has become so good, these rogue agency, the one generating this counterfeit note, had become so good that the police and them are living peacefully in that equilibrium. The police doesn't know that there are these notes and they're able to get by. Right? So this is what we are talking about when we talk about the GAN. So the idea is to make two networks, the generator and the discriminator, compete with each other in a mini-max game, right? So this is the generator, the crook, and this is the discriminator, the police. The generator or the crook tries to fool the discriminator or the police by creating more and more realistic images, in this case banknotes, and the discriminator, the police, tries not to be fooled by the generator, the crook. So again, what we actually do is we put a low dimensional vector into our generator. That's the input, right? So this is our low dimensional Z. So Z can belong to, let's say, R of 100. So it's a 100 dimensional vector. The size of would be 100 cross 1. And now we have these, which are our data set images. So this is our data set. And this is what the generator is generating. So initially, when the generator is not trained, when we input random noise, this will also kind of be very random, right? One thing to note is that the dimension of this is higher than Z. So Z is a low dimensional vector of size 100. Let's say this is a high dimensional vector of size 32 cross 32. Right? So it's at least 10 times bigger. 32 cross 32 is 1024. And so this is what the generator network looks like, right? So the generator network is straightforward. And what is the input to the generator network? The generator network, the input is a simple noise vector Z of size 100, let's say. And then what is the input to the discriminator? The input to the discriminator are images. The images can either come from the data set or the images can be generated by the generator itself. We usually call the images generated by the generator fake images and the images of the data set real images. And the goal is to make the fake as close as the real as possible. And the discriminator, what does it do? It basically says, okay, if it's an image from the data set, it says real image. If it doesn't look like an image from the data set, it says no. So it's a binary classifier, can be trained using our regular cross entropy, right? So training the discriminator is very straightforward. What are we doing? We are in a batch putting, let's say, a bunch of real images, so a bunch of these real images and a bunch of these fake images. And then for each image in the batch, we have corresponding targets. The initial targets can all be, let's say, zeros corresponding to real image, and then the second half can all be ones corresponding to fake image, or vice versa. So the training of the discriminator is straightforward, like what we have been doing so far. But now listen carefully. This is where I'll tell you how to train the generator, and this is where it becomes implicit. It is not explicit. Why? Because we train the generator using the gradients from the discriminator. When we are training the generator, we don't need the dataset images. We only need the images generated from the generator. We put them into the discriminator and we flip the label. We say that this one, we want the output to be real, right? So we minimize the loss of whatever is coming out here and real, right? So we put a negative log on this because we want the real to be high. Why? Because we are asking, okay, I'm using images from the generator, but I want them to be real. So what is the loss what will it take for me to have less loss? I want to minimize that loss, right? I want to go in that direction so that I start to output real. And to do that, we then want to, that is our loss, right? So our loss when we are training, so when training the generator, like here, so we are now training this generator, and when training the generator, we flip the loss, right? So we flip the label, because though this is though this should come here, right, because it's a generated image, we want this to be high, and then we compute the loss of this, right, and then we back propagate that. So we back propagate the gradients, but we do not update the weights, right? While doing the backward of the discriminator using this flipped label, we do not update the weights of the discriminator, because that will be wrong, because then you will be teaching the discriminator something wrong. Instead, what we do is, we don't update, we just use the discriminator to do the chain rule. We take the gradients at the input of the discriminator and we copy it to the output of the generator. And note that the output of the generator and the size of the input of the discriminator will be same, right? So now we have the gradients, and the gradients are the size of the output of the generator. And here we again use chain rule and back propagate within the generator, and the weights we actually update, right? We do the derivative of loss with respect to the weights, and with that we update the generator. And that's all that there is in generative adversarial networks. Of course, we'll go through like a lot of detail, we'll look at code, but the intuition is just this, right? So we have a generator and a discriminator. You train the generator, you throw away the discriminator, but you train the generator first, right? You train it to be able to distinguish between real and fake images, and then you use the discriminator. Of course, you train both of them together, a few iterations of the discriminator, then a few iterations of the generator. So you train the discriminator a little bit, and then you take only images from the generator, you put them into the discriminator, and then you want the real to be true, you compute the loss, you back propagate, you do not update the weights, right? You do not update the weights when doing the training of the generator. You copy the gradients over, and then you update the weights, right, of the generator, and use chain rule to back propagate within the generator. And that's all that there is.